So we should now record the session.
Yes, there is.
So I tried again to upload the PDF and see this time it works.
Yes. Yes, we can see it.
Okay.
Okay, should I start introducing?
Yeah, I think so.
Yeah, sure.
Okay, so welcome everyone. Good morning, good afternoon, everywhere in the world that you're listening to us. I have the honor to start this series of the seminars on topological quantum computing. So this is the joint organization seminar by Sebastian Halbig and Shawn. And we are very happy to have Shawn as one of the main organizers to start today by giving us the roadmap, an overview of topological quantum computing. And hopefully in the following weeks, we will focus on the more deeper to the different topics that is connected to topological quantum computing. So if you have any questions, please feel free to write it in the chat, and I am very happy to give the camera to Professor Shawn. Please, thank you.
All right, thank you very much. Let me see if I can make this into full screen. Okay, can you see my screen right now?
Yes.
Okay, that's great. Thanks a lot for the introduction. Hi everyone, welcome to the online seminar series on topological quantum computing. I'm Shawn. I'm an associate professor at Purdue University. Per the request of my fellow co-organizers, I'm going to give an introduction to topological quantum computing, but you should take this as a starter, it doesn't contain much new results. It's more of a review to the field of topological quantum computing. But hopefully for the next couple of weeks and months, you will see different talks about a different perspective of the subject. Also a big a disclaimer before I start. Just because of the limits of the time and also my own capability, it's going to be a partial introduction, so I can't possibly cover all the topics of TQC. So if you miss some topics, don't be frustrated, and hopefully you will see them in the following talks. Okay, I want to start with some basics in quantum computing to motivate the need for topological quantum computing, and then I'll outline the rest of the talk. So the idea of quantum computing originated from the early 80s when Feynman and Manin proposed to use the idea of to use quantum systems to simulate another quantum system, essentially utilizing the principles of quantum mechanics to do calculations. And soon after that, Deutsch gave a framework for the quantum Turing machine, and even developed a quantum algorithm which is exponentially faster than any classical algorithm. Albeit that particular algorithm is not quite useful. But the next real theoretical breakthrough came in the 90s when Peter Shor came up with a quantum algorithm to factor integers, which is believed to be exponentially faster than classical algorithms. Many of you may know, this factoring integers is the backbone of public key-based in cryptography. For example, here this RSA-260 is, this is a 260-digit long integer, and if you can find factors of this integer, you can likely break someone's account and then steal some information. Okay, so before talking about quantum computing, let's start with the model of classical computation. Classically, information is stored in the bit string of 0s and 1s, and the information is processed by applying quantum logic gates, such as the AND gate, the OR gate, and the NOT gate. In quantum computation, in quantum computation, the bit is replaced by a quantum bit or a qubit, which abstractly is just a two-dimensional Hilbert space with a orthonormal basis, which we denote by the ket0 state and ket1 state. Multiple qubits is formed by taking the tensor product of several copies of C2. A quantum state is a unit vector in the multiple qubit state, which is defined up to scalar multiplication. For example, the 1 qubit states, we have the 0 state, the 1 state. We can also form a superposition of the 0 state and 1 state. For multiple qubit states, we can take the tensor product of the 0 and 1 states, which is the quantum analog of the classical bit string. But there are also other quantum states, like this one at the bottom right corner. This is a 2 qubit state. You can check this is not the tensor product of two 1 qubit state, and we say it is a entangled state. Okay, now in quantum computation, the states are modified or processed by unitary transformations and are acting on the multiple qubit space. They are called the quantum gates. For example, this X gate is a 1 qubit. It is a gate acting 1 qubit, which flips the 0 and 1 state. The Harmart gate in the middle, and also the CNOT gate is a 2 qubit quantum gate on the basis states. It maps the state, the basis state I comma j to I comma I plus j mod 2. And similar to the classical circuit, we also represent quantum gates by a circuit with incoming wires and outgoing wires. Each wire represents a qubit. Another ingredient in quantum computation is the measurement, which is basically the way to read out the quantum states. More precisely is a probabilistic operation on quantum states. Say we have a quantum state psi, which is the superposition of the 0 and 1 state. By measuring the state, we get either the 0 state or the 1 state with a probability, which is proportional to the norm square of the coefficients in front of the basis states. More generally, there's a more general notion of measurement, which consists of a complete set of orthogonal projectors P. Then by measuring a state with respect to these projectors, we end up with a state which corresponds to projecting the initial state using one of the projectors in the measurement, again, with some probabilities. So the process for quantum computing is then as follows. We start by preparing some initial states, which typically is a product of some simple states. And then we apply a sequence of quantum gates to modify the states according to the algorithm. And then eventually we read out the state by making a measurement. Always good. Well, except in the real world, the qubits via the abstraction of quantum systems. For example, a spin 1/2 particle, where a spin up state corresponds to the 0 state, a spin down is the 1 state. We can form a chain of multiple spins, but the spins will inevitably interact with the surrounding invariant. For example, causing one of the spins to be flipped. Another factor is there is imprecisions in how we can control the system. Maybe we want to rotate the spin by 120 degree, but in fact we can only execute a rotation, let's say 120.001 degree, for example. All of these introduce errors to the system, to the calculations, and when they accumulate enough, they will destroy the computing process. So a standard approach to dealing with this issue is to use a quantum error correction code. Namely, we can encode a logical qubit inside multiple physical qubits. Let's say I can just take 3 physical spins and then to encode 1 logical spin. Then let's assume that the error is now 2 terrible and it flips one of the spins. Then you can detect the change and then correct the error. Of course, this is like a toy example of an error correction, but the fact is that there exist more sophisticated error correction schemes that can correct arbitrary errors. But this is not what I'm going to focus today. Instead, what I'm going to focus is the hardware approach, like in contrast to the quantum error correction, which is the software approach. The hardware approach is the topological quantum computing, which is what I'm going to focus on. So for the rest of the talk, I'm going to talk about I'm going to talk about TQC from 3 perspectives, namely from the topological physics matter, higher category, and topological quantum field theory aspects. And by the way, if you have any questions, feel free to interrupt. If you Okay, so let's consider some identical and elementary particles located at the, let's say, the positions x1, x2, and xn. Such a configuration is represented by a wave function, psi of x1, xn. Now, because they are identical, so if we swap the labels of 2 particles, then they should represent the same configuration, which means they should be represented by the same wave function up to a global phase. E to the I theta. Now, if theta is pi, so the phase is -1, then the particles are called fermions. For example, electrons, protons, neutrons, quarks, the elementary particles that make up matter, they are all fermions. It turns out they have half-integer spins. For theta equals 0, the particles are called bosons, those including photons or Higgs boson and so on. And they all have integer spins. It turns out in the 3-dimensional world, all the elementary particles, they are either fermions or bosons. However, the collective behavior of these elementary particles, they could have some exotic feature that arise from the interactions of them. Just as the famous quote, more is different. So let's consider the following setup. For a collection of electrons constrained in the 2-dimensional plane with a strong magnetic field in the vertical direction at very low temperature. Now, in such a system, first of all, there's a robust gap between the ground state and the first excited state. So it's a gapped quantum system. And moreover, the excited states, they behave like quasi-particles that can be localized and separated. And they can also be move around and fuse together, for example. And they obey more general exchange statistics. Let's say if we have some identical quasi-particles in the plane, represented by some wave function, then if we swap some 2 of them, then the wave function undergoes a unitary transformation, represented by this operator u. So here u, it could be a phase, but the phase doesn't have to be 0. The angle doesn't have to be 0 or pi. It could be a more general phase. But even more exotically, it doesn't have to be a phase. this U could be a higher dimensional unitary matrix. And these features characterize the so-called topological phase of matter, and we call this quasi-particles anyons. Let me give you another like a toy model, maybe a concrete model for topological phase of matter, the so-called toric code. Consider a spin system on a lattice where we assign a qubit on each edge. So the total Hilbert space is the tensor product of the physical qubits. The Hamiltonian H consists of two types of terms. This A sub V for each vertex V and BP term for each plaquette P. More precisely, given a vertex V, the AV acts by the so-called poly X operator on the qubits adjacent to the vertex V. And similarly, this BP operator acts as the poly Z operator on the qubits on the boundary of the plaquette P. It can be checked that these operators, they square to identity and they commute with each other. So these operators, they have either +1 or -1 eigenvalues. The ground state of the Hamiltonian is the common +1 eigenspace of these operators. And now let's consider excitations in such a system. I can apply a sequence of the Z operators, the poly Z operators, along a path in the lattice. This is called a string operator. If I apply this string operator to a ground state, okay. Well, first of all, here are some properties of this string operator. You can check that it commutes with all the plaquette operators and also commutes with all the vertex operators, except at the ends of the string, where it anticommutes with the AV, the vertex operators. So that means if we start with the ground state, omega, and we apply such a string operator to the ground state, then we will end up with the excited state, which has an eigenvalue of 4 more than that of the ground state. So essentially, we have created, we created a quasi-particle excitation at the end of the string. And similarly, we can also apply a sequence of the poly X operators along a string in the dual lattice, and then it creates again a pair of quasi-particles at the end of this dual string. Okay, now let's see what happens when we move around these quasi-particles. So let's apply this blue string operator to a ground state. We get a pair of here. There's a black quasi-particles in the lattice, and then we can move around these particles by successively applying another string operator. They remain in the same excited space, like with the same energy. Let's also create a pair of pink particles. And then also, by the way, on the left column, you will see the calculations of the state. But at this point, you can ignore some of the details. So now let's try to move one of the black particles around one of the pink particles by applying this string operator around the pink one. Then by some straightforward calculations, it can be shown that the final state differ from the initial state by a -1 sign. So essentially means that the relative phase resulted from the process is -1. And furthermore,
Sorry,
this case is...
Can I ask a question? Is the orientation important? How do you go around the pink point?
In this example, it doesn't matter. But in general, yes, the orientation matters. But yeah, in this example, it's -1 in either orientation. Okay, and moreover, this negative sign is robust as we deform the process, as we deform, the path of the strings. So that's so it has a robust -1 sign. Lastly, we can also try to fuse these quasi-particles. Assume we have created some pairs of quasi-particles using the string operators. And then let's say we can bring a black particle close to another black particle, then they will annihilate to the vacuum. And similarly for the pink particles. But if you try to bring a pink particle with a black particle, then they will survive and then become a composite particle. So this illustrates the basic ideas in a topological phase of matter. But there are also other concrete lattice models realizing topological phase of matter. For example, if you fix a finite group G similar to the model I discussed, you can define a lattice model, exactly solvable lattice model, realizing topological phases. I'm not going into details of this, but I believe the next talk by Steve will include topics on this model. But in this general model, two new phenomena arise. First of all, the fusion of two quasi-particles, they can result in different types of quasi-particles, different from the previous model. Also, the so-called non-rAbelian Aronoff bomb effect, which means when you swap two quasi-particles clockwise, then they behave differently from the swap in the counterclockwise. So that's the again, this feature doesn't arise in the previous model, but they could arise in the general case. Okay, so let me comment briefly on on the potential sources of anyons or quasi-particles we can find in practice. The most prototypical source for anyons is the so-called fractional quantum holes, like the example I gave about the collection, the two-dimensional electrons. Under some conditions on the magnetic field and temperature, then we can find the contact hole conductance, and it is believed such systems host quasi-particles or anyons. Also, the spin so-called quantum spin liquid, some exotic magnetic materials. These materials, even at zero temperature, these spins they are still disordered, and instead, they form a so-called topological order. In more recent years, there are lots of efforts in trying to simulating or implementing these topological states on current quantum processors across a wide spectrum of platforms, including the superconducting qubits, the trapped ions, the neutral atoms, and so on. But because of the limitation on the available qubits and then the lack of error correction, so now this is more like a proof of principle than a genuine, a realization of topological phases. Okay, so now let me show how we can perform quantum computing within anyon system. The qubit is we encode qubits or states in the global degrees of freedom of multiple anyons. For example, the fusion channels of some anyons. Because these are the global degrees of freedom of these anyons, the information is not accessible by local and small perturbations. For example, by just perturbing an individual anyon, that cannot disturb the information encoded in the global degrees. And there's an energy gap between this configuration with the rest of the spectrum. The quantum gates are realized by swapping swap of the anyons or braiding of the anyons. Namely, we can adiabatically swap some of the anyons in the space-time trajectory, in the space-time dimensions. This process traces out a diagram which is called a braid diagram, and this process induces a unitary transformation acting on the multiple anyon space, and those are the quantum gates. It should be noted that these quantum gates are robust against the local deformations of the swapping process. And so that's what that means. These braiding of anyons are inherently fault-tolerant. And lastly, the measurement is obtained by fusing these anyons one by one back to the vacuum. That's essentially a readout of the final quantum states we obtain. So parallel to the process of quantum computing, in TQC, we start from the vacuum. We create some pairs of anyons to initialize the system to get initial state, and then we braid these anyons in some sequence to act as quantum gates, and then eventually we fuse these anyons back to the vacuum to make a measurement. This way of quantum computing was proposed by Kitaev and Friedman in the late 90s and early 2000s. Okay, that finishes my first part of the introduction. I'm gonna move to this to the part of algebras. But before I go, is there any question? Okay. All right. So I want to describe.
I'm sorry. Can I ask you a quick question? Sorry to interrupt. Experimentally, are there any instances of those non-Abelian anyons that were observed in some condensed matter system? Or?
Right. I mean, of course, there is lots of ongoing efforts to find non-Abelian anyons in the experiments, and sometimes it depends on what you mean by finding a non-Abelian anyon. But as I mentioned, the fractional quantum hole is one of the prototypical sources for anyons. And as far as we know, this like a Abelian anyons. I'm sorry, I haven't talked about Abelian and non-Abelian, but just to answer your question, the Abelian anyons have been confirmed experimentally with no doubt. And I think non-Abelian anyons are a lot more challenging to either confirm or even to engineer or even to confirm the existence. But again, so there are different potential candidates to realize the non-Abelian anyons.
Okay, thank you.
Okay, so I want to describe an anyon system with some a set of data, like as a characterization to the anyon system. And algebraically, this is described by the so-called a unitary modular tensor category. And I'm going to talk about this structure with some discrete set of data. Now, in this slide, the red part represents some structures in the modular tensor category. And I'm going to point out what they correspond to in the anyon system. So in an anyon system, it could host different types of species or quasi-particles or anyons. We label them by A, B, C. These correspond to the sample objects in the category. Among them, there's a special one, namely the vacuum or nothing. We denote that by 1. That's a particular anyon. It corresponds to the tensor unit in the category. Also, for every particle A, there's an antiparticle which we denote by A bar. Next, the fusion rules. When we fuse two anyons of type A and type B, then in general, it could result in different possibilities of outcomes. So we record the different possibilities formally in terms of the fusion rules. Namely, for an anyon of type C, we use the integer NABC to encode the different ways of fusing A and B to result in C. For simplicity of this talk, I'm going to assume NABC is either 0 or 1. If it is 0, it means that C is not a possible outcome. Otherwise, it is a possible outcome. The state space encoding the multiple anyons, let's say A1, A2, AN, with a total type C, this corresponds to the home space in the category from the object C to the tensor product of these anyons, A1, A2, AN. In particular, if we consider two anyons, AB with total type C, the home space or the state space is one-dimensional, and we choose the basis in this space and represented by such a graph here at the top. You can think of this graph as a physical process of splitting the anyon C into two anyons, A and B. And this is called a splitting tree basis or a fusion tree basis. Then we can consider more processes involving more than two anyons. Let's say we can start from a anyon D. Okay, we split D into some intermediate anyon X and C, and continue to split X into A and B. Alternatively, we can split D into A and some intermediate anyon Y, and continue to split Y into B and C. These two ways of splitting give us two bases of the state space of three anyons, A, B, C, and they are related by a matrix change. We call the entries of this matrix change the F symbols. And similarly, if we consider two anyons A and B, and then if we braid this anyon A with B, then we end up with another state, representing two anyons B and A. This new state differs from the original state by a scalar. We call this scalar this RBAC, and that's called the R symbol. Now, these F symbols and R symbols, they satisfy lots of constraints and some compatibility conditions known as the pentagon equations and the hexagon equations, but I'm not going into details on these equations. But the point is that these fusion rules and the F and R symbols, together with the conditions they need to satisfy, encode the data of a unitary modular tensor category or an anyon system. Here are some quick examples of modular tensor categories or anyon systems. I've talked about the toric code. It supports 4 anyon types: the vacuum, a E particle, M particle, and a composite particle, EM. Here we have the fusion rules. And more general, in other cases, we have the Fibonacci anyons. So in this system, in addition to the trivial anyon, there's only one non-trivial anyon, tau. And you see the fusion rule is particularly interesting. When you fuse two tau anyons, you end up with either the trivial anyon or the tau anyon. There's also the Ising anyon systems, and also a sequence of theories. They're denoted by SU2 level K, where K is a non-negative integer. In such a system, the anyons are labeled by integers between 0 and K, and they also satisfy some particular fusion rules, which we know. Okay, so one of the questions you might ask, given an anyon system, is if you build a topological quantum computer out of it, then how powerful it is. This is related to the universality question. Recall that in TQC we encode qubit or qubit in the space of multiple anyons. Let's say I take n anyons of type A with some total type B. Then asymptotically, this space, as n goes to infinity, the dimension of this space behaves like a d sub A to some to the power n, where d sub A is a real number. And d sub A is called the quantum dimension of the anyon A. In particular, if it is 1, then this anyon is called a Abelian anyon. If it is greater than 1, then it's called a non-Abelian anyon. Okay, also we know the quantum gates arise from the braiding of the anyons. Mathematically, these quantum gates, they form a representation of the n-strand break group. Here, Bn represents the break group with generator sigma 1, sigma 2, and sigma n-1. The action of the generators, for example, sigma 1, the first generator acts by swapping by braiding the first and the second anyon, and similarly for the other generators. We say an anyon A is braiding universal if for some anyon B, and then for the number n large enough, the image of this break group representation is dense in the unitary group of the state space. That means if it's universal, it means you can apply braiding to approximate any quantum gate in this QD space. A classical result in this direction is the following. So for this sequence SU2 level K, as long as K is not 0, 1, 2, and 4, then the result of Friedman, Larson, and Wang showed that a particular anyon, which we call the type 1 anyon, is breeding universal. Now, recently we have a partial strengthening of the above result. Namely, if we instead of just braiding, if we just restrict ourselves to the so-called double braiding, which means you only like allow us to swap, like to drag a particle, an anyon, around the other particle. That's called a full braiding or a double braiding. Then we can show that at least for 1 qubit, then the double braiding is already universal. Mathematically, this means that the braid group representation generated by the generators sigma squares is dense. And so we found this result more recently, but later on we find that this result can also be derived from an earlier paper of Simons, Bonstein, Friedman, and so on from earlier. Okay, the remaining cases in this sequence, we have 4 remaining cases. The k equals 0, 0, 1, 2, and 4. When k equals 0, this is the trivial phase. It's nothing interesting. K equals 1, this is called the Samian theory, which consists of only Abelian anyons. So in terms of TQC, it's not quite useful. K equals 2 corresponds to the so-called Ising anyons. And it is believed that the anyons in this system is classically simulatable efficiently. So it doesn't offer quantum advantage. The remaining case is k equals 4. I'm going to spend a minute to talk about this case. So in SU2 level 4, again, if we take 4 anyons, I'm going to take 4 anyons of type 1 each, and assume their total type is 2. Now, it turns out the corresponding state space is 3-dimensional. I'm going to denote a choice of a basis by 0, 1, 2 state. So that's a Q trait. And then to get 2 Q traits, we're just to take 8 anyons and partition them into 2 groups, for example. But it's known that in this system, the braiding of these anyons is not universal. In fact, you can only get a finite group of quantum gates. It is not braiding universal. But if we can make use of some extra operations, in this case, for example, if we are allowed to measure the total type of 2 anyons, then that's some extra operation, and which can bring some extra power to the system. And it turns out that in this case, such a measurement effectively is equivalent to a measurement that projects the state to either to one of the basis states or the complement, the orthogonal complement of that state. A fairly old result we can show is that in this case, if you allow this total charge measurement, then the system is universal for quantum computing. And we call such a type of universality a resource-assisted universality. So here's the landscape for the computational power of these anyon systems. The Abelian anyons, for example, the toric code, they're useless just in terms of braidings and so on. They're useful for other purposes, such as a quantum memory. But just in terms of braidings, they're useless because the state space is 1-dimensional. Now, but even inside the non-Abelian anyons, they fall into different hierarchy. All right, we know that this SU2 level K for most values of K is braiding universal. So that's as best as you can hope. But on the other extreme, the Ising anyon, we know or expect that it is efficiently simulatable on a classical computer. So it doesn't have any quantum advantage. But in between of these two classes, we have this resource-assisted universality, such as the SU2 level 4. And also, there are lots of work on regarding the resource-assisted universality on the so-called double S3 model, and so on. These anyon systems, they sort of offer a intermediate or intermediate stage for universal quantum computation. So I'm just gonna throw out some quick open problems in this general subject. For example, can you classify the anyon systems or unitary modular tensor categories? This is a big open problem. It's like the classification of finite simple groups, for example. And so far, it's been completed either to rank to 6 or rank 12, depending on what you mean by classifying, like classifying up to equivalence or classifying up to some restricted set of data. But roughly, this has been done for anyon systems of a small rank. Here, the rank means the number of anyon species in the system. Regarding the universality, there is the property F conjecture by Naidu and Rowell, which means that which states an anyon has a finite group, Brit group representation image, even only if its quantum dimension squared is integer. It's a surprisingly simple statement of the conjecture, but remarkably, the conjecture has been verified to be true for all known examples. But the complete proof remains open. Another question is about the characterization of the resource-assisted universality. Right now, we only know some examples of such systems, but there's a way to characterize such anyons. For example, are they related to solvable anyons or nilpotent anyons? Okay, another problem I want to address is the so-called the existence of leakage-free breeding gates. So in general, in TQC, the qubit is the state space of multiple anyons, but this state space in general lacks a tensor product structure. It's like in the standard quantum circuit model, we have the tensor product of qubits, but in TQC, usually such a structure does not exist. So in order to get a multiple qubit space, we need to choose a tensor product subspace within the multiple anyon space. Schematically, we take a collection of anyons, maybe partition them into different groups, to form the first qubit and then the second qubit and so on. But the problem is that as these subspaces, they live in the larger space of multiple anyons. When we breed these anyons, well, sometimes it's good. For example, if we breed anyons within the same group, then it just induces a unitary transformation on that qubit. But if we breed anyons from different groups, then these only induces a quantum gate or unitary transformation on the larger multiple anyon space. It doesn't necessarily preserve the multiple qubit space. So the problem in general is we have to choose the sequence of breedings carefully in order to avoid leakage, so that the breedings does preserve the multiple qubit subspace. Just to take the Fibonacci anyon system as an example, let's take 6 anyons of type tau. The first 3, group them into the first qubit, and then the last 3, the second qubit. Then we have a 2 qubit subspace living inside the space of 6 anyons. But it turns out that this space of 6 anyons has dimension 5 rather than 4. Because, well, in addition to the computational basis of the 2 qubit subspace, that depending on the total charge of some pairs of anyons, there is an additional non-computational state within the space. And then this is the fifth, essentially the 5th dimension in the multiple, in the 6 anyon space. We say a breed is leakage-free if it preserves the 2 qubit subspace, and we say the gate is entangled if it is not the the tensor product of 2 1 qubit gate, or a gate of that form followed by a simple swap of the 2 qubits. For example, the signal gate, as I mentioned earlier, that's an entangled state. but x tends to z, that by definition is not an entangled state, an entangled gate. A problem is in this Fibonacci model anyon system, is there a leakage-free entangled bridging gate? Just want to report some result. So we have some study of this problem, and we still don't have an answer for that problem. But here, so this is just some partial report. We can show that any braid diagram composed of the following building blocks is leakage-free but non-entangling. So you can form quite complicated braid diagrams. They're leakage-free, but what you get, the gate is pretty boring. We also numerically emulated all the braids up with the length up to 10, and we still find no leakage-free entangling gates. So it seems likely, and also I guess that's the conjecture to most experts in this subject, is that maybe in this Fibonacci anyon model there doesn't exist leakage-free bridging gates. So just a quick remark. So we know if you consider the three anyon models, the Fibonacci anyons, the SU to level 4, or the easing anyon, the Fibonacci is a breeding universal. SU to level 4 is resource assisted universal, but the easing anyon is not universal at all. In contrast, for the leakage-free entangling gates, we know, and I didn't show the details, we know that in SU to level 4, such gates, such breedings exist, as well as in easing model. They both exist, but in Fibonacci anyons, this conjecturally does not exist. So there seems to be a tension between the two properties of anyons. So I'm just going to formulate this into a conjecture. An anyon is a breeding universal if and only if it doesn't support leakage-free entangling gates. Okay, so all right, and now I'm going to move the last part very quickly to talk about the topological aspect of TQC. So if we consider, we talk about these anyon systems or lattice models, but these systems, they don't have to live in the plane. In general, we can define the model on an arbitrary surface, let's say a surface M. Then the state space, then the ground state space on such a surface that's a topological invariant. It's stable under local perturbations, and we call that an invariant of the surface. We denote that vector space by V of M. So for any surface, we associate the space of ground states. And then for any space-time manifold X, let's say whose boundary consists of two surfaces M1 and M2, you can see a picture on the right. Then we can start, because we think of X as the space-time manifold, we can consider the transition amplitude from a state psi1 in M1, a ground state psi1 in M1, to another ground state psi2 in the state space of M2. This transition amplitude defines a linear operator from the ground space of M1 to the ground space of M2. We call this linear operator Z of X. And this assignment, V of M and Z of X, they satisfy some conditions. For example, the ground space of the distant union of two surfaces, they should be given by the tensor product of the ground space of each surface. Also for the linear operators, they satisfy the so-called gluing axiom, which means we have a space-time manifold X and Y, which share a common boundary M2. Then you can glue these two along the boundary M2 to form another space-time manifold. And the gluing axiom says the operator associated to the glued manifold, it can be obtained from the linear operator of both X and Y. So to extract these properties, and we can formulate the notion of a TQFT axiomatically. Namely, for integer d, a d plus 1 dimensional TQFT is a symmetric monoidal functor from the category of of d plus one dimensional cobordisms to the category of vector spaces. And essentially that means the assignment in particular to any closed manifold, d-dimensional manifold M, we assign a vector space V of M, and for any cobordism X, we assign a linear operator Z of X. In particular, if X is closed, which means it doesn't have boundary, then the operator Z of X is operated, defines a linear operator from the one-dimensional Hilbert space, and such a linear operator is just a scalar. And it turns out this scalar is an invariant of the manifold, and that's called a quantum invariant. Also, if you're given a diffeomorphism phi on the closed D manifold, if we denote M sum phi to be the mapping cylinder associated to the diffeomorphism phi, then the linear operator associated to the mapping cylinder defined is operator from the state space of M. And in fact, this defines a representation of the mapping class group of the manifold M. So the quantum invariants and representations of mapping class groups, they are the product of the result from a TQFT. In the 2 plus 1 dimensions, there are two fundamental families of TQFTs, the so-called Reshetick-Trife Witten TQFT, constructed from a modular tensor category. These are like generalizations of the Jones polynomial of knots. And also the trivial Baird-Westbury TQFT, constructed from a spherical fusion category. And a classical result in this field is that these two TQFTs are actually related to each other. So namely, if you take a fusion category C, then the trivial Baird-Westbury TQFT essentially is the same as the Reshetick-Trife TQFT, but constructed from the so-called dream field center of the input fusion category. One of the open problems in this field that relates this TQFT to topology, the so-called volume conjecture, volume conjectures, because there are different versions of the conjectures. Here's one version. If you consider some like a modular tensor categories, specifically it's called the TLJ or Template-Lipper-Jones category. It has a parameter indexed by the so-called Kaufman variable, which is a relativity. Then for any closed oriented hyperbolic three manifold M, and if you vary the parameter R in the Kaufman variable A and let R goes to infinity, then the conjecture states that the Reshetick-Trife quantum invariant of the three manifold M, it behaves roughly like the exponential of the hyperbolic volume of the manifold. So you may be more familiar with the volume conjecture for knot, for hyperbolic knot, but this is the version of the conjecture for hyperbolic three manifold. Okay, some quick comments about TQFTs in 3 plus 1 dimensions. In 3 plus 1 dimensions, there also exist topological phases of matter, but because in the 3 plus 1 dimensions, in the spatial 3-dimension space, the point-like excitations or the anyons, you can argue that they can only be fermions or bosons. So the exchange statistics are pretty boring. However, there could exist more interesting excitations.
Shawn?
Yes.
Sorry, I think we have a question.
Yeah, go ahead. Can you read? Because I can't see the question.
I can only see a raised hand.
Okay.
So,
what's the question?
Yeah, I'd suggest if you type a question in the chat, I can read it out, but right now there's just a raised hand. So I'd say Shawn can continue and then I'll ask him the question later.
Okay. I mean, can they speak? I mean, do they have the function to speak?
Yes, sure.
Okay, okay. But we can, yeah, I guess I'm going to finish in a few moments. Yeah, so in the three, but yeah, in 3+1 dimensions, there could exist more interesting excitation that are not point-like but string-like. Maybe the excitations live on the link, for example. Take the simplest example of a like an on link, like several circles which are not linked to each other. These are sort of like the generalizations of the point-like anyons, but now they are string-like. We also consider the exchange statistics for excitations of this form. Now, in this case, instead of a Brit group representation, these multiple component on link, they form the so-called loop Brit group, and so the braiding of these excitations induces a representation of the loop Brit group. The algebraic theory of these topological physics matter are generally believed to be related to higher categories, more precisely this braided monoidal 2 categories, which include special cases like ribbon categories or spherical fusion 2 categories, and so on. For 3+1 dimensional TQFTs, one important application of that is to construct the TQFTs which provide powerful invariance of 4-dimensional manifolds. By powerful, I mean like the invariance that can distinguish smooth structures of manifolds. For example, the trivisual type construction of TQFTs from fusion 2 categories done by Douglas and Realtor. But there's a limitation to such TQFTs because of the no-go theorem, which states that semi-simple TQFTs are not able to distinguish smooth structures for manifolds. And so we have to go beyond semi-simplicity and consider non-semi-simple TQFTs. Here I'm just going to list some partial list of efforts in this direction. With my collaborators, we have constructed some non-semi-simple invariants of 4 manifolds based on Hopf algebras. There's some TQFTs constructed from skin theories of non-semi-simple ribbon categories. There's some construction of some special construction, like not invariants of 4 manifolds, but rather something called a 2 handle bodies, also constructed from ribbon categories. More recently, there's the so-called the construction of the skin Lassanian module, motivated from the Kovalnov homology, and then this is not quite a 3+1 TQFT, but you can still see it has some features of TQFTs, and then this invariance is shown recently to be able to distinguish different smooth structures. Okay, so I guess that's more or less what I want to say, and just as a summary or like a take-home message for my talk, I just want to say, this TQC is related to the, among other things, is related to the 3 parts, topological phases, higher categories, and TQFTs. I want to emphasize that each of them is a huge subject as well, and what I talk about today is really on the surface of everything. And maybe a final remark to my talk. I mentioned that the TQC, the hardware approach to fault tolerance, in contrast to the software approach of error correction. But in practice, really, there's no clear distinction between these 2 approaches. For example, in a sense, you can argue that in TQC, this topological phases of matter itself serves as a quantum error correcting code. From a different perspective, I could say, even for the software approach, like some of the best quantum error correcting codes, they actually arise from the ground state space of topological phases. So really, these 2 approaches are related to each other. And also, in practical TQC, you can argue that still active error correction is required. For example, maybe you break these anyons too fast, and then it's non-adiabatically, which could result in some unexpected excitations. But even if you do adiabatic braiding, there could still be thermal anyons and imperfect isolation of these anyons and so on, all of which can introduce errors to the system, and some degrees of error correction is still needed. I just want to end my talk with maybe a philosophical comment on the relation of of the two approaches for the tolerant quantum computation. So essentially, whatever approach you implement, for tolerance seems in one way or another related to the topological protection. And with that, I'm gonna start my talk. Thank you.
So thank you so much for the nice talk. So we have two parts of the questions. We have the recording, if you want to ask the questions, and then we'll stop recording for people that are shy to ask. So please unmute yourself and ask if there is. It was some question from Alex, I guess.
Yeah, I guess Alex, you can speak.
Yeah, it wasn't my question. I think it was, I don't know. I remembered the name. Yeah, no, it wasn't my ask.
Okay. Sorry, then I was mistaken. So, okay, so if there is not any urgent question from the audience, maybe I can ask myself a question. So, could you tell us about the in algebraic language? What is the understanding of this leakage-free braiding gates that you had? I mean, do you have any algebraic understanding of that, about this leakage-free?
Right. I mean, algebraically, it is simply right. You have a unitary modular tensor category, and the braiding operation induces a braid group representation on the on the Helm space, right? On the Helm space, from some object to the tensor product of some identical objects. So naturally, you have a braiding on that Helm space. But in practice, I mean, for the purpose of quantum computing, you always need to choose a subspace from that Helm space, and the braiding only act on the larger space, on the larger Helm space, but not necessarily on the subspace that you choose. And then, of course, that depends on how you choose your subspace, right? In rare cases, the Helm space itself has a natural. I mean, the dimension is, let's say, is a power of 2, for example. And in certain cases, there's a natural choice of a tensor product structure. So in those cases, the whole space is the multiple qubit space. So there's no problem of leakage. But in generic cases, you have to choose a proper subspace, and you need to make sure that you only consider those braidings that preserve the subspace. And then the question is, like, if there exists even one braidings that preserve the subspace and act interestingly, namely it acts as a entangled gate, but rather than just the product of some one qubit gate.
Thank you. So Matthew, please.
Yes, thank you very much for the nice talk. It was very understandable. Just a quick question about this conjecture you made in the second part of your talk. I think it relates to the previous question. This tension you mentioned between universality and non-leakage. It seems like a very harsh conjecture, no? From the point of view of the task one wants to achieve, no?
Right. So the only evidence I have is backed by the numerical calculations and some examples I have. I think in a sense it's similar to the property F conjecture. If you which states right on one end is the image of the brick group representation, and on the other end, it's just the quantum dimension of this single anyon. And the thing is particularly simple. And then so I guess this this leakage-free conjecture is similar in the spirit to that conjecture. So I don't have any intrinsic, like intuition, like why this conjecture has to true. Is rather from like a numerical evidence.
Okay, thank you.
So Uli, please.
Yep, can you hear me? Yes,
Yes.
it seems so. So my question is more basic. I didn't really get this this definition of what leakage means, to be honest. Can you say that again?
I'm sorry, the definition of what?
What leakage means, I didn't understand that concept. So what is this leakage problem about? I didn't get that.
Yeah, so let me see if there's an easier way to navigate to. No, okay. Yeah, I'm just gonna say. So
I don't think so.
Yeah, okay, that's fine. So the point is, like you want to do quantum computation with your within the computational subspace. So you have a subspace inside a larger space, and then at some point you have your state is within this subspace, which is good. That encodes the information you want to work with. But if maybe at some point some operation will bring the state to outside of the subspace, okay? It just means you get the state outside of the subspace unintentionally. That could happen in TQC because the operations you do, like the braiding of the anyons, they occur in the larger space. So they don't always preserve the subspace. I mean, pure, in terms of linear algebra language, it's like you have a linear operator on the larger space. And initially you have a vector, you have a state inside the subspace, but this linear operator can bring the state outside of the subspace, and that is called leakage.
Okay, so would these subspaces be, say, if they are eigenspaces of some operator, and if your braiding doesn't commute with that operator, for example, would that be an example?
Yeah, well, no, I mean they're not necessarily the eigenspace. As I mentioned, usually is by choice. So you choose a subspace within a larger space. Of course, there are some kind of standard choice, and this one I think I can go back fairly quickly. Hold on a second. Okay, yeah. So here, yeah. So here, so you see, I have 6 anyons, right? The larger space, the ambient space is the state space of 6 anyons. But to choose the subspace, I group the first 3 and then enforce. Well, actually, that's a bad example. Maybe the previous slide. Yeah. So I group. If you look at the top figure, I group the first 3 and then require the total type of the 3 anyons to be tau, and also group the last 3 anyons and then require that their total type is tau. So essentially, I choose a subspace with the restrictions on the subset of anyons. These subspace, is, you can say it's eigenspace of some braidings, but not all braidings. Yeah, I'm not sure. Yeah, I'm not sure if this answers the question.
Okay, yeah, I think so. Thanks.
Yeah. Okay. Are there other questions?
I would suggest I turn off recording now, so all the questions you want to ask non-publicly, we can do now.
Yeah, I may ask one last question before we stop the recording. Your last slide, you had this keyword called topological protection. Could you maybe add a few sentences about it?
Yeah, I guess so. That's again, that's like a philosophical remark, I would say. So topological protection, I guess generally, I guess what I meant is that either you do topological quantum computing or standard fault-tolerant quantum computing with quantum error correction. The fault tolerance is basically due to some topological properties of the way you do computation. Like in the TQC, right? That's the topological protection from the topological phases. And in standard fault-tolerant quantum computation, is because the quantum error correcting codes you use, they are, at least some of them, or like some of the error correcting codes, they arise from the topological phases, or they work well because they are because like the logical space of the quantum error correcting code arise at the ground states of topological phases. So that's what I meant in general. Like in one way or another, it's related. Like the protection is related to the topological properties of your system, which makes sense, right? Because topology, by definition, is it's the property that don't change on the deformations, and those deformations in physics, they correspond to local perturbations, which means if you encode your state in topological properties, then they are bound to be resilient to local perturbations.
Thank you so much. So thank you so much again for the nice talk. So we have stopped the recording. So feel free to ask the other questions that you have. Thank you, everyone.